Good day. Welcome once again to yet another session for mathematics. Over the past few weeks, we have looked at a whole array of concepts, starting from indices to logarithms to variations, as well as simultaneous equations. Now, let's take a step back. Let us consider yet another important pillar of mathematics that every other aspect or most of the other aspects build on. This is the concept of trigonometry. Now, do not forget, mathematics at every level across all disciplines would always have a basis. On that basis, we will then build every other concept and relation. The same thing applies for the concept of trigonometry. With the use of trigonometry, we then move on to other kinds of concepts, including geometry, including every other vast area of mathematical shapes that you have. Now, what exactly do we mean when we consider or talk about the concept of trigonometry? From the word tri, we are talking about a three-sided shape or three things. When we now say trigonometry, we are simply then talking about the study of these three-sided shapes. Now, in our elementary classes, we have already learned the concept of plane shapes, or at the very least, we can diagrammatically distinctively show the differences between them. We know what a square is, we know what a triangle is, we know what a rhombus looks like, we know what a kite looks like, we know what a parallelogram looks like. All of these are plane shapes. In particular, what you call the triangle is simply a three-sided shape, right? So you have something of this form. So it has a side here, another side here, and another side here. Now, this triangle is in fact the basics for whatever we are going to be studying in trigonometry. So the focus for this class will be to talk about the basic laws, operations, or structures that guide whatever we do on this three-sided shape we call triangles, right? In this lesson, we will talk about one of the most common laws of trigonometry that we know, which we call the Pythagoras theorem. From there, we would also talk about some trigonometric rules, which you refer to as the trigonometric ratios, and then we will look at how exactly we can use this concept in other plane shapes, not just the triangle, but in other plane shapes you can have. So let's begin. Today, we'll be looking at the trigonometric rules. Trigonometric rules. Now, just as we mentioned, for these trigonometric rules, we are simply talking about trigonometry, right? Which essentially is talking about triangles, right? Which are three-sided shapes. Now, do not forget, as far as the concept of triangles are concerned, there are vast amounts of concepts that can be discussed in the concept of triangles. Some of which is, what are the types of triangles we can have? How can we categorize these triangles based on their angles and, of course, based on their sides? We will be talking about that briefly, and then we will then move on to look at what are the rules of engagement that guide these triangles. So let's continue. Now, for triangles, we will talk about, first and foremost, the fact that you can classify them based on the angles or based on the sides. Whenever we have a shape such that every single angle within it is less than 90 degrees, we will say that that triangle is an acute angled triangle. Of course, if we also have a triangle where at least one of the sides is greater than 90 degrees, at least one of the sides is greater than 90 degrees, then we can call it an obtuse angled triangle. And if we have a triangle such that at least one of its sides or one of its angles is exactly 90 degrees, then we will call it a right angled triangle. These are the common classifications that exist as far as triangles are concerned based on their angles. Now, of course, elementarily, we have discussed the concept that whenever you have an angle that is less than 90 degrees, it is called an acute angle. Any angle that is greater than 90 degrees is called an obtuse angle. And then any angle that is exactly 90 degrees is called a right angle. So for instance, you have a straight line. Do not forget, the angle on a straight line is exactly 180 degrees. 180 degrees angle on a straight line. Now, from this angle on a straight line, we then move on. If we split this angle such that we consider theta in this form, then theta is less than 90 degrees. We will have it as an acute angle. If we consider the other side, this side, which is obviously now going to be greater than 90 degrees, let's say we call it beta. Beta is obviously greater than 90 degrees. Then we'll say beta is an obtuse angle. And then what happens when on that straight line instead, we are considering half of the angle on the straight line. The entire angle on the straight line is 180 degrees. So what happens when we are considering half of it? When we consider half of it, then we'll be talking about, let's say we have this to be phi. Then phi, which is 90 degrees, will then be called a right angle. So these are very, very important concepts, right? These are concepts we have talked about so many times as far as mathematics is concerned in elementary levels. Acute angles, obtuse angles, right angles, angle on a straight line, angle at a point. The angle at a point is exactly 360 degrees, right? And so on and so forth. All of this serve to allow us increase that concept. So building on the concept of these angles, we can also talk about the triangles and their classification based on the angles. Now, why can we do this? This is because the total angle in a triangle, the total angle or the total sum of angles in a triangle is exactly 180 degrees, right? So if you add up the three angles of the triangle, this one, and this one, the sum of all of them, let's say we have it to be A, B, and C. The sum of A, B, and C will exactly be 180 degrees, right? So the total sum of angles within the triangle is 180 degrees. So this first one is saying A, B, and C are each of them less than 90 degrees. So A is less than 90, C is less than 90, B is less than 90. It's called an acute angle. This one is saying if either A or B or C, if one of them is greater than 90, then it's an obtuse angled triangle. And then this one is saying if A is equal to 90, or B is equal to 90, or C is equal to 90, then you can call it a right angled triangle. These are very, very important concepts you should keep in mind. Now that we have looked at a very good foundation on what trigonometry stands for, which is on the concept of triangles themselves, let's now move on into what is our main focus for today. Now, let's continue. Based on this concept, let us now extend. Of course, we have talked about the angles. On the part of the sides, you would also find out that we can also classify it into 3 types. We talk about the equilateral triangle. We can also talk about the scaling triangle. And of course, when you consider these kinds of triangles, they are very, very important because they all have their own properties. The equilateral triangle, what does it tell you about the sides? The scaling triangle, what does it tell you about the sides? Every single triangle you have their own base condition. It is very, very important you realize and understand how those base conditions work. There are some triangles in which all their sides are equal. There are some triangles in which only 2 of the sides are equal. And then there is also another kind of triangle where all of the sides are not exactly equal to one another. All of these types or kinds or categories of triangles play significant roles as far as the concept of trigonometry is concerned. You would find out that the moment we start talking about the rules that guide trigonometry, you would also then find out that these rules are hugely dependent on the kind of triangle we consider. For instance, for the Pythagoras theorem, which we'll be considering first, you'll find out that for the Pythagoras theorem, the most important basis is that the triangle must be a right-angled triangle. That is the first condition. And then for sine rules, cosine rules, which you would also consider later on, you'd find out that this time around, it being a right-angled triangle is no longer significant. However, there is importance in the amount of angles that are known and the amount of sides that are known. These are very, very important definitions that we must adhere to. So, first off, let us consider the Pythagoras theorem. For the Pythagoras theorem, we have said the first condition, which is the most important one, is first, a right-angled triangle. First off, right? The Pythagoras theorem next condition is that it looks at the relationship between the sides, right? So it's a right-angled triangle first and foremost, and then what the Pythagoras theorem considers is the relationship that exists between the sides. This is very, very important. Now, how then do we talk about this relationship? Consider a right-angled triangle. Let us talk about what it means to be a right-angled triangle. For it to be a right-angled triangle, first off, it must have a right angle. That is the angle that is exactly equal to 90 degrees. First condition. Now, let us name this triangle ABC. A, B, and C. From this triangle, first most important thing is for this right angle that you have, the side that is directly opposite that right angle is what we call the hypotenuse. That is the very first angle that places you in direct presence with the very first side. So the 90-degree angle is the first angle you notice. And the side directly opposite the 90-degree angle is what we call the hypotenuse. Keep that in mind. Now, Pythagoras now says that, okay, fine, I have gotten that hypotenuse, right? How then can I talk about the relationship that this hypotenuse shares with the other 2 sides? Other 2 sides meaning this place, Abi, this line, let's represent by C, and then this line, let's represent by A. Let's call this hypotenuse side B. right? Small letters. The angles are usually denoted by capital letters, and then the sides are usually denoted by small letters. Now, Pythagoras' theorem now states that the square of this hypotenuse, which is the side that is the very first to come out, the square of this hypotenuse is always equal to the sum of the squares of the other two sides. Which means once you can find the hypotenuse, the square of that hypotenuse is always equal to the sum of the squares of the other two sides. What does this mean? I'm saying the square of the hypotenuse, that is b squared, right, is equal to the sum of the squares of the other two sides. That is a squared plus c squared, right? A and c are the other two sides. So the sum of their squares is going to be equal to the square of the hypotenuse side. This is what the Pythagoras theorem postulates. And this is very, very important. So that is the relationship that exists between the two sides. We are saying in general that, yes, once you can identify the hypotenuse, and you can always identify the hypotenuse with the right-angled side, right? The right angle will be directly opposite the hypotenuse. Now, once you have that hypotenuse recognized, the square of whatever the hypotenuse value is will be equal to the sum of the squares of the values of the other two sides, which is very, very important. Now, this concept of Pythagoras theorem has played very, very large roles as to how we carry out operations regarding triangles, but not just triangles, but in fact other plane shapes that share similarities with triangles. And it is very, very important. Now, one thing that Pythagoras theorem directly leads us to as like corollary is the fact that from your Pythagoras theorem, you can easily detect some perfect squares that will satisfy the theorem. We call these perfect squares the Pythagorean triples or the Pythagorean triplets, right? Pythagorean triples refer to a set of numbers that are each perfect squares. That is, they are whole numbers, their square is also a whole number, and they fit in perfectly into the Pythagorean theorem. A good example of the Pythagorean triplet is 3, 4, and 5. This is a very, very good example. Why? Because, of course, first off, another point of note, the hypotenuse will always be the longest side, right? It is also always facing the 90-degree angle, but more than that, it is always going to be the longest side out of the three of them, right? So 5 squared, which is our hypotenuse, has to be the sum of 3 squared and 4 squared. And if you verify this, this is essentially true. 5 squared is 25, 3 squared is 9, plus 4 squared, which is 16. 9 plus 16 is also 25. This is a good example of the Pythagoras triplet or the Pythagorean triple. Very, very important. Another good example is if you have 5, 12, and 13. This is another Pythagorean triple. Here, if you take 13 squared, which is obviously 169, you will have the same thing as 5 squared plus 12 squared, because 5 squared is 25, 12 squared is 144, 25 plus 144 gives you 169, which is 13 squared, right? So these are triples. Triples are very, very important. Pythagorean triples are very, very important because it easily allows us draw up any simple triangle, any simple right angle triangle, such that their sides will conform with the Pythagoras theorem. A good example is I can simply quickly draw up 3, 4, and 5, 3, 4, and 5 based on the right angle. Of course, I can place 3 and 4 anyhow.